Yes, I am a postdoc at Wrapup, and David is director de recherche, I believe, and this whole thing is situated in Grenoble in France, right? Okay, so like in general terms, our work is about a new relational abstract domain for programs that have both Boolean and numeric variables, right? And so one of our sort of starting motivations was to deal with programs, to deal with array manipulating programs, right? So for example, if you look at the program in this slide, right? So what it does, it fills an array, it initializes the array from E going from 0 to n. You assign something to array of I42 in this example, right? And the loop invariant that would allow us to later prove the properties would be I goes from 0 to n, k goes and for all k that goes from 0 to I, array of k equals 42, right? So we have kind of two cases here, k less than I, then array of k is filled, and then k greater than I, array of k is not filled, it's unconstrained, or whatever it is, right? And then we can actually make this program understandable to like even the simplest abstract interpreter possible by applying this technique by David Magnier and Lorgoner. And there are multiple versions of this technique, but basically what you do, you replace arrays with auxiliary variables. And in this example, there is an auxiliary variable k, which denotes some index into the array, and a variable ak, which denotes the value at index k, right? And what a transformed program in this example would do, so it would say that, well, there is this index k that goes into the array, and then in the loop, if our index I is equal to this k that we're tracking, right, then array of k equals 42. So, and we can go even further, and we can help the analyzer by doing some trace partitioning manually. And we introduce this Boolean variable b that we set to true when we initialized the array element, right? And then, in order to analyze this program, now we just need a relational domain that would be able to, in which we would be able to say that, well, I is between 0 and n, k is between 0 and n, and then if b holds, then k is less than I, and array of k is equal to 42. Right, so now we need a domain that can work with such abstract states. So, okay, like if we make a step back and kind of forget about Booleans just for a little bit, so we could use this these linear decision diagrams. So basically, it's a family of abstract domains of slightly different flavors, and basically you would be dealing with a decision tree where the nodes are linear constraints. And there are multiple versions of that. So one of the latest ones is by these authors back in 2009. And then there is a full implementation for non-relational constraints, as far as I remember, sort of boxes domain in Crabble LVM. But then, so we wanted Booleans for some other reasons as well, so we kind of skipped on that. Then what we did actually use for a while is this BDD-apron domain by Bertrand Genet. So I think, unfortunately, there is no publication corresponding to that, but this is developed by Bertrand Genet, and what BDD-apron can do, you can have elements of the form, right? So B1, B2, and so on are disjoint Boolean formulas, and P1, P2, and so on are apron polyhedra, right? And you can have an element that says, well, B1 and polyhedra 1, or B2 and polyhedra 2, and so on, right? And then so this has two possible representations, either as a list of pairs or as an empty BDD where polyhedra lives. And I think both implementations are pretty similar in terms of performance and properties. So, and then with BDD-apron, what we would be able to do, we would be say B and things that hold when B is true, or not B and things that hold that when not B is true, right? So this does work. So there is kind of slight unfortunate issue with BDD apron is that the number of polyhedra you're going to deal with in a single element is going to be exponential in the number of Boolean variables that you have. And you do hit these cases quite often, especially so when you have programs like this that have sequences of conditionals where you need an observer variable for each conditional. Right? So there is this kind of program here, right? At every step, you take a choice, you assign on one branch, you assign false to a variable, on another branch, you assign true to a variable, and you do a slightly different thing on the two branches. Right? And then in this case, when you try to analyze this, you get 8 polyhedra in the end, in the element. And then the thing is, most often all these polyhedra would be more or less similar, except for these few constraints that you actually manipulated on this path. Right? So that's kind of unfortunate, we thought. And kind of the proposal was that maybe we wanted to keep, Okay, so the proposal was that maybe we would allow every linear constraint to be labeled by a Boolean formula that enables it, right? So now what we want to deal with, we want to have our abstract element to be a sort of a conjunction of implications. B implies C, right? So where C is a single linear constraint and B is a Boolean formula. Right, so for the case of array filling, like our first example, then we would be able to express an element like that. Right, you see true implies I greater than 0, true implies I less than n, and so on. Everything that is true for all cases. And then there would be specific cases for specific constraints that that need to hold only when B is true. B implies k less than I, B implies AK equals 42. Right, and then this sort of series of conditionals, this previous example would be if B0 holds, then X0 should be less than 1. If B1 holds, blah. If B2 holds, so. Right, so basically, we kind of want that the constraints that are shared between different variations of Booleans, they are not repeated multiple times. That's what's kind of the idea, and maybe this would work. So, and then we say, okay, we will just see, like we can make this work, right? So we can see whether the algorithms for constraint-only representation of polyhedra would be able to adapt it to work with this, right? And then there is quite some work on constraint-only representation of polyhedra. So recently it works by David Magnier and Mikhail Piran and their students. So there was Alexey Bakhirkin, there is Alexander Marichal who defended recently. They were developing this Wrapup polyhedra library, which is based on constraint-only representation. Then there were works of Andy King, and I will mention more people in the slides. So, all right, but indeed, it's not very difficult to adapt more simple algorithms for constraint-only representation to work with this kind of constraints. Right, so when we will eliminate a rational variable, we will adapt Fourier-Motzkin elimination. When we will do join, we will adapt projection-based convex hull. Elimination of Boolean variable is using join. Assignments are straightforward. Widening would be adaptation of standard widening. So, okay, the part here is how do we eliminate redundant constraints, and this is for now more of a thing for future work, but I mean, we do it soundly, but not very smartly, I guess. Okay, so another interesting feature of this whole thing is that most operations, they, well, if you will, distributive evaluations of Boolean variables, in a sense that if you did this big case analysis and produced this polyhedron and split this element into a single polyhedron for a single assignment of Boolean variables, then applied the base polyhedral operation, whatever projection or join or whatnot, to these individual cases, and then collapsed everything together, this would be the same result as applying these modified versions of these algorithms, in most cases, except some. So this is a nice feature in the sense that you don't lose precision by just having Boolean variables without doing any any tricky things with them. Okay, so we'll go quickly one by one through the operations and see how they roughly work. Okay, so the original Fourier-Motzkin elimination, what we would do, we would take our polyhedra and we would split the constraints, right? So we're eliminating one variable. In this case, it would be x. So we would split the constraints into constraints that where x appears positively. Well, when we sort of direct the comparison in a certain way, right? X would appear positively in one set of constraints, x would appear negatively in another set of constraints. Then we produce all pairs of constraints, and then we combine them in a way that removes x. So in this case, the left one we would multiply it by 3, the right one we will multiply it by 2, take a sum, then the result is 7y greater than 0. Well, obviously we can divide by 7 in the next step. So this can be optimized for equalities, right? So if a variable appears in an equality, you use it as you can use it as a definition, basically do Gaussian elimination. So this is what, well, from what I know, this is what VPL Wehrmacht Polyhedra Library 1.0 does. So Alexey Bakhirkin wrote a whole thesis about, well, not only this, but about how to make this work reasonably well. And sort of the claim is that it, like, despite this algorithm being like the more naive one, it is claimed to actually work. So kind of the trick here is that, right, so now as you eliminate one variable, you can square the number of constraints, and most resulting constraints are actually redundant, so you have to remove redundant constraints regularly when you do this, because usually you eliminate not just one variable, but a whole set of variables. So now when we have these Boolean, when we have these Boolean labels, now we have B implies one constraint, B2 implies another constraint, and then what would be and how do we combine them in the result? And the thing is, so this left constraint is only enabled when B1 holds, and the right constraint is only enabled when B2 holds. This means that their combination is only enabled when both B1 and B2 hold, right? So this means that when we combine the two constraints, we can join the Boolean parts, right? And then kind of the rest of the points, they kind of still hold for that. So, okay, join. So we base what we do on the algorithm by the described in these two papers. Well, hopefully I got the years right, but so in these two papers. And so the original idea there is that every point in the convex hull of two polyhedra is a convex combination of a pair of points, one taking from one polyhedron, another taking from the other one. And so what we do here, right, so lambda 1 and lambda 2 are going to be the coefficients for the convex combination, right? So they are both non-negative, their sum is equal to 1. So y1 and y2, right, so we had these points, x1 and x2, 2 points. Well, so x1 and x2 are vectors representing points that are in the first and the second polyhedra. So in our system, y1 and y2 would be x1, x2 already multiplied by lambda, right? So x equals lambda 1 x1 plus lambda 2 x2, meaning y1 plus y2. And then we take the original constraints of a polyhedra and multiply them by lambda, right? And we get a 1 y1 greater than lambda 1 d1 and so on. Right, and now when we eliminate y1, y2, lambda 1, lambda 2, okay, so this is not elimination of 4 variables. y1, y2 are vectors of variables, and lambda 2, 1, lambda 2 are single variables. Right, so when we eliminate all of the auxiliary ones, we get a set of constraints over X, and that is the topological closure of the convex hull. And then, right, so this thing always only contains non-strict inequalities, and then Alexey, in his thesis, he says how we can recover the strict ones when we need, because we can, every resulting inequality we can track back to the original ones, and we can track back and express as a combination of the original ones, and this way we can see which inequalities actually have to be strict in the result. So adaptation of that to Booleans, it's kind of just a bit tedious to write. I didn't put it in the slide, but it kind of goes around the same lines. We see which inequality should be enabled in the result, in which case. Right, so there would be some sort of Boolean formulas inserted here and there, and constraints become implications, but it's not a kind of big deal. So, okay, eliminating redundant constraints. Okay, this is kind of a weak part now. Okay, so they have to be eliminated regularly, right? And what we do for now, we're going to just ask an SMT solver if a constraint is redundant. Right, so just as it would be in the case for convex polyhedra. So if we have a set of constraints D and we ask, well, if B implies C is if it is redundant in D, and then you want to ask, do other constraints in D imply B implies C, right? And then when you rewrite it as a SAT query, you say, well, you flip the constraint in D and see if the result is unsat, right? So B and not C, and D without B implies C. If it's unsat, then the constraint is redundant. Right, so obviously there are, so this is complete, right? So there are incomplete checks that we need to do, or we can do, before we get to before we resort to this point. And so one thing that we have, or we can do, is we can see the constraint is implied by one other constraint, right? So this is incomplete, but this eliminates some redundant constraints. And actually, in the simpler cases, it would eliminate most redundant constraints. Okay, and then like if we go to other operations, so I think I'm running, oh no, I'm not running ahead of time. Okay, so, okay, other operations, just briefly, so elimination of a Boolean variable, it's one of the few over-approximate operations, right? So because you use Booleans to separate polyhedra, and when you remove a Boolean variable that would distinguish it to polyhedra, you have to take the convex hull, right? So kind of on a high level. Okay, this is straightforward, right? So when you say exist B Boolean B in D, what you want to do, you want to replace B with true on one side, replace B with false on another side, and join the two things, right? So linear and Boolean assignments are as usual. You do renaming, you do add constraints, you do existential quantification, and so on. Invertible linear assignments are, again, by substitution, are kind of a little bit less obvious thing that we can do in this domain is we can do linear to Boolean assignment. We can assign to a Boolean variable the result of a linear, or the value of a linear inequality. For equalities, it's more tricky. You cannot store a result of an equality in a single Boolean variable. You need to split into two inequalities and store the value of equality in two Boolean variables. But you can do this. Then there is inclusion test. Well, for now, we also ask an SMT solver for that. So, okay. Widening is remaining, and it's also kind of similar, but maybe a bit more interesting. I put it on a separate slide. Right, so what was the original widening? One way to do widening with just convex polyhedra, right? So you have D1 included in D2, and you say, well, let's take, for every constraint in D1, let's see if it is redundant if added to D2, and if it is, you add it to the result, right? So now, I mean, so it's cute just as an exercise, right? And then now, how do you lift it to Booleans? Well, you take a linear constraint, like a linear part of some constraint in D1, and you ask, well, for which Boolean formula B implies C is redundant in D2? And well, there's more than one approach to this, but one way to do it is you can do it using projection. The paper describes it in more detail. I guess it's just a nice exercise. Okay, so in the paper, I don't think we prove that this is widening, and but I think you can prove it again by this argument of distributivity over Boolean relations of Boolean variables, right? So you would fix some arbitrary relation of Boolean variables and see that the result of this operation is the same as if you applied the operation on the underlying sort of basic underlying convex polyhedron. Okay, so we did implement this, right? So we have this abstract interpreter for constraint horn clauses, and there is a paper about, or rather, there is a paper about the theory behind what we do and why this whole thing exists separately. So we published it in SAS 2017, but well, thanks to some administrative procedures, I couldn't go. But then actually I got a chance to present it at HCVS. It's a workshop on horn clauses for verification. I'm quite happy about that. So yeah, so that thing already can use BDD apron, and now it can use this abstract domain. So to represent Boolean formulas, we use BDDs, in particular the code package. As a SMT solver, we use it 3.4.5, so later versions, unfortunately, well, I didn't investigate it yet, they time out on many queries that we produce, although the formulas look actually quite benign. And then the 3.4.5 almost never is kind of a weird thing now, right? Almost never times out. Okay, results. There are things that we're kind of happy and not happy about. Okay, like on the more theoretical level, you know, well, I mean, we had all these things coming, right? So we had them coming just to spell them explicitly. Right? So in this approach, or at least yet, you cannot, you know, separate equalities and inequalities really and make use of it, well, except some corner cases when you have like true implies some equality and then you use that one for Gaussian elimination. So outside of that, you cannot have like, you know, canonical representation of polyhedra and anything similar because, well, because between different relations of Booleans, there is no common system of equalities. So that's kind of unfortunate. We cannot apply any methods or heuristics or whatnot based on anterior point, on finding an anterior point. So there is, again, this work by Mikhail Piran, Alexander Maréchal, where they pick a point in a polyhedron and they do things with it. It's again, no common anterior point between relations of Booleans, and it's all this. These two things are really unfortunate, kind of makes us want to rethink maybe some of the decisions that made kind of on the way. Okay, in terms of implementation, now it's about 5 to 7 times slower than BDD apron I will mention a bit what these examples are. So most of the time, I mean, again, we had this coming, right? So most of the time I spent asking SMT solver about redundant constraints. And actually most redundant constraints I eliminated before the SMT calls by sort of incomplete, well, not heuristics, but incomplete methods. Right, so what we related this with, so we took a few programs from this, the competition, from the simpler categories, it's like loop and recursive, and we use this tool, C-Horn by Ari Gorfinkel and some other people, and it translates C programs into horn clauses. And then you can analyze them. Then we have some handcrafted programs pretty much, which are mostly results of this array removal thing, but also just some corner cases that we wanted to test. Okay, where this has to go, right? So this has to, we have to get rid of an SMT solver somehow, and well, I mean, we will. I'm not sure how yet. So another nice thing to try is to reduce the number of calls to full redundancy elimination, right? So now we use things that can say, well, okay, this constraint is surely redundant because it's implied by another constraint. There is another category of these, well, heuristics or checks that says that, okay, this constraint is surely non-redundant, and in particular there is this ray tracing technique, but we cannot quite apply it yet, but maybe we could apply something similar. There is this ray tracing technique by Alexander Maréchal, where you pick a point in a polyhedron and you should trace, and whatever first the ray hits, like the hyperplane, so that thing is irredundant definitely. So things like that would help. I guess on the high level, it would be nice in general apply more recent algorithms from constraint-only representation. So again, Alexander Maréchal, he defended his thesis recently, and he has this projection based on parametric linear programming, a mouthful, which is apparently works quite a bit better than Fourier-Motzkin. And then again, they have this ray tracing heuristics and whatnot, which apparently help quite a bit, but we couldn't apply them quite yet. But yeah, I guess that is it. And thanks for listening.
It looks like an example of a cardinal product. You had the same question?
Cardinal product. I mean, I'm not prepared to answer your question, but that could be.
Okay.
I mean,
Yeah, it's called a cardinal product or reduced relative power, or another flavor is intuitionistic implications domain.
All right.
So
Okay.
you can build a systematically new domain by adding implication as you did for your domain.
Okay, I imagine this.
And so you get for free some way of obtaining transfer functions, and so maybe it's related to what you did.
Well, I imagine this influenced probably the original idea, right? This is work of more than one person, right? It's me, David, and there were other people kind of who came up with the original idea, or probably they knew this underlying theory. Yeah.
So if the answer is yes, you can do a paper next year where you replace Polyhedra by anything and you will have a domain constructor.
That could be.
But for the implementation of the operations.
You said that when compared to BDD prone on those benchmarks, you were 5 to 9 times lower, 5 to 7 times lower. And the question is, how many disjunctions are there on those benchmarks?
Usually few. So in these the comp programs, like 1 to 2, right? I mean 0 to 1, if you will. In the handcrafted programs, it can. So there are programs that have, I don't know, 8 disjuncts, 16 disjuncts, but it's not many. We don't have a big set of benchmarks that would exercise the sort of.
So that might be one of the reasons why, because your compressed representation doesn't perform very well.
Yeah, I guess. Yeah, so I guess in a way the goal of this work to see what is the baseline performance of this whole thing and can we push it towards, you know, being viable, because I guess at the start of this work these numbers were like 10 times higher, or like it was 50, 70, and then we did some work to actually make it 5 to 7, and I guess after that we can indeed switch to, you know, more meaningful benchmarks that, you know, exercise the motivation. Yeah, I mean, I agree with the point. The benchmarks that you see here, they don't quite exercise the motivation that we state. Yeah, this is true.
Is the restriction to using a constraint-only representation an essential part of the proposal, or I mean, it's orthogonal to the fact that you use a constraint-only or a dual representation?
Well, I guess yes and no, right? If I imagine, okay, I imagine we went this way because we kind of already knew what we would do with operations, while if we tried to insert, to add this, to produce this reduced cardinal product of double representation of polyhedra, I guess we wouldn't know what to do, because we would need to make a modified version of Cherenkov algorithm or whatever it is, and we would have, you know, system of constraints with constraints implied by Booleans. We would have a system of generator where every generator is enabled by a Boolean. I mean, that would be interesting thing to see how this would work, but I guess we didn't know where sort of to start, so we went with kind of what we knew should kind of work.
Okay, thank you.
Are there more questions? If not, let's thank the speaker once again.
Thanks.